Alright, so let's try to summarize what we've learned in this section. We looked at parallel loops like parallel for and parallel for each. We saw the fact that they are all essentially blocking calls, which means that you would block on them, you would wait for all the threads to complete, or you would wait until somebody maybe cancelled or broke out of the parallel loop, or maybe an exception has occurred. We looked at the fact that as the parallel loop is executing, you have an access to the variable of type parallel loop state, which lets you know what's going on with the other tasks in the loop. It basically tells you, for example, whether the loop has already been stopped. We also saw that after executing a parallel loop, you can check the result of the execution in a parallel loop result. For example, you can find out whether all the tasks that were supposed to be processed were in fact executed or not. And finally, we saw that using parallel loop options, you could customize the actual execution process for the parallel loop. We saw that you can specify the maximum degree of parallelism or provide a cancellation token. We looked at parallel invoke, which is just the idea of running several provided functions concurrently. It's basically the equivalent of creating a task for each function or each lambda that you provide and then doing a wait all on all of the tasks. And of course, it does involve starting the tasks, forgot to mention that. And then we looked at parallel for and parallel for each. So parallel for is essentially a counter which uses an index from start to finish. The finish is exclusive, so if you want to count from 1 to 10, you need to put the terminal variable at 11. We saw that this cannot provide a step, so you cannot do a for loop where you take all the odd numbers, for example. You have to provide a custom enumeration for that and then consume the enumerable using parallel for each. We saw that you can partition data into different tasks, and we saw the customization that this involved. And we looked at the fact that the parallel loop executes each of the provided delegate, passing in the counter value as the first and only argument, which sometimes is inefficient, and sometimes you don't want to make this many delegates essentially. So we also looked at parallel for each, which is just like parallel.for, but it's for any kind of IEnumerable. So you feed in an IEnumerable, and the partitioner then tries to sort of spread out the tasks according to how many elements you have in the IEnumerable. And keep in mind that sometimes the IEnumerable does not give you the count originally. So if you take a list, for example, yes, it will tell you how many elements there are. But if you take something which is a function which just does a bunch of yield returns, you're never going to find out how long the total number of elements is. So that's something to watch out for. Then we looked at a more complicated idea of thread local storage. And basically, we saw the example where we had lots of tasks writing to a single shared variable. And we saw that this situation can be optimized by doing partial evaluations in each of the tasks. And then when you have evaluated the task on a certain number of items, then you can collate the results and then specify a function to integrate these partial results into the final result. So that's also very useful. And finally, we talked about partitioning, the idea that as you execute something in a parallel loop, the entire data set is split into different chunks by a partitioner. And this idea that you can create your own or specify what kind of partition you want. And the goal of this whole thing is to improve performance. For example, if you have lots of costly delegate creation calls, you can avoid those by processing some of the data in ordinary for loops in different threads. So that's it when it comes to parallel loops in .NET.